And welcome to our official start of data structures for today. I'm going to do a quick recap of what we talked about last time. And really the purpose of last time was to sort of set us up for what we'll talk about today, which is going to be the material that you actually need for the homework assignment. So if the concept of classes was still a little bit fuzzy after last time, that's okay. Today is really the material that you'll need for the homework. And so I'm sharing my screen right now. And sort of the first big example that we talked about last time was this duck and the dog class. And this is sort of like the classic Python example for using classes because it leads into this joke right here that everybody in Python likes, that if it walks like a duck and talks like a duck, then it is a duck. And so Python, we say Python uses duck typing because of this expression right here. And when I was doing this last time, so I've switched over to the terminal. I'm in my week 8 folder for the class repo right now. And inside of here, there's a bunch of files. And the one that we're going to look at right here is ducktyping.py. When I was doing this last time, we'd created this duck class and this dog class and did a bunch of stuff, but eventually I got to a spot where the syntax wasn't working out for me. And so we'll just quickly revisit that to see what the correct syntax was. The main things, though, to remember from these classes was there's that if you have a function that's defined inside of a class, we call that function a method. So it is both a function and a method. Every method is a function, but not every function is a method. And then if you have these special methods that have these double underscores in front of them, you can call them double underscore methods or dunder methods or magic methods. Those are all synonyms for the same thing. And each one of these magic methods has its own special meaning. This init magic method is the constructor of the class. In Python, it's, I guess people kind of 50-50 call it either init or constructor. But if you're talking classes in the abstract outside of Python world, everybody always says constructor. And then this repr function was sort of like a way to generate a nicer way to visualize the class, that without this, you just got kind of a junk looking output, didn't tell you what's actually inside of the class. And all of these functions, whether it's a magic method or not, one thing that they have in common is that they take the self parameter as the first parameter to the class. And this self parameter is how you actually access the contents of the class. So we said our duck had 3 attributes. Recall that an attribute is a variable that is part of a class. And so again, every attribute is a variable, but not every variable is an attribute. And the way that we access them is you do self dot and then the attribute name, and that will let you either assign a value to it or read a value from it. So we defined this duck class and this dog class, and they're very, very similar. The only difference was that the ducks quacked and the dogs barked. And then we had code down here defining, say, Donald Duck and Daisy Duck using the constructors like this. Again, every time you call, so here, duck right here is the name of the class, the thing that came after the class keyword up here, class duck. And then when we use this name of a class as if it were a function, it's not a function, but we use it as if it were a function by putting these parentheses around it. This calls the constructor, calls the magic init method or the dunder init method for us, and creates an object of type duck and assigns it to the variable Donald. So there's a lot of sort of key vocabulary words that I'm repeating over and over again as we do this. In this class, you're never going to have an exam where I'm going to ask you to define what is a method or what is an attribute. I'm never going to test you on something like that. But throughout the rest of this course, I will be using these terms, and it's important just to have a working knowledge of what these terms mean. So here, created this ducks list of Donald and Daisy and just looping over it and calling the quack method on the duck like this. And it prints out the quack method for Donald and Daisy. Down here below, we'll go ahead and just run this code just to see what it does. And so here, line 20 is this top printing all these equal signs. And then here, for duck and ducks, Donald, Daisy, quack, my name is Donald, quack, my name is Daisy. Then next we created a dog. This dog constructor had no parameters to it. So a constructor can have, just like any other function, 1 parameter, 0 parameters, an arbitrary number of parameters. And here, because the dog had no parameters, we had to assign it a name specifically by using the attribute just like a variable. So Lassie.name equals Lassie this way. And then this was the line that I wasn't able to get working last time. And what I had written before was something like this. I kind of tried a couple of different variations of this, but this is actually what I should have written right here. And what this is doing is it's creating a quack attribute on Lassie. And recall that every function is just a variable, so every method is just an attribute. And here is what the variable or the attribute is assigned to be equal to. I'm gonna just really quickly describe what this is. If the details don't make sense to you at this point, that's okay. I'd be happy to, if you're curious, go over and like the excruciating details in office hours about what's going on here. But it's also not something that you'll need, say, for the homework assignments to understand in detail what's going on here. But basically what this is so the lambda creates an anonymous function. We've seen that before. Previous anonymous functions that we've created had arguments that were passed to them. This one does not have an argument being passed to it. And here we're doing duck.quack and passing in Lassie. So this right here is equivalent to having created a quack method up in the dog class like this. But now instead of every dog getting the ability to quack, only Lassie will get the ability to quack, because we're adding it only to Lassie right here and not to all dogs. And now we can loop over the ducks plus Lassie like this and call the quack method. And now everybody's going to quack, including Lassie. And it's one of the sort of like big picture takeaways from this about how Python compares to other programming languages is that in other programming languages that you may have used before, especially Java and C++, two that are used in, say, the AP computer science exams, are also very popular in first year programming courses. In all of those other programming languages, the programming language cares about the type of the class. And in Python, we never care about the type of the class. We never care if something is a duck. We never care if it's a dog. We don't care what it is. We don't care whether something's a list or a deck or a queue. We don't care. And if it's possible to make your code write in a way that it does care. And if you do that, you're doing something that we'd call unPythonic. It's not technically wrong. It's just bad style and something that other Python programmers will not like. Instead, we just care about, does it have the functions that we want? And if it does have the functions that we want, then we just use it, and that's it. So again, if anything in this explanation didn't make sense, or you have questions about it, I'm happy to go over that in more detail in office hours today. But we'll be seeing another example today that's actually more concretely, directly related to your homework assignment. And I think that will also help maybe fill in some of the gaps about when to use classes and what they're good for. The other thing that we talked about last time, scrolling down here, was that there are sort of these 4 different ways to exit a function in Python. And so we've seen the return call before. That's sort of like the standard way to exit a function. This is something that every programming language has implemented. And these other 3 down here are things that not every programming language has implemented. And so we saw last time just the syntax of this yield function, that anytime you have return, you can just replace it with yield. And I explained at a high level that the difference between these two is that in return, after you call it, you'd say the control flow never comes back to the function. But with yield, it's sort of like it only temporarily pauses the function, and control flow will return back to the function in the future. And we just did a really quick example of that, and it's yeah, not expecting you to fully understand this at this point. So what we're going to do in class today is we're going to talk about more classes in the object-oriented programming sense, and in particular about this iter and this next magic method. These two methods are, we say that if a class implements these, then the class is an iterable class. And so things like lists, index, and all the sort of data structures, all the containers that we've seen so far, they implement these. And we'll see that these have a very close connection to for loops and how for loops work in Python. We'll also see that this yield keyword is just syntactic sugar for the iter and next magic methods. And so once we talk about these two things, we'll see exactly what that syntactic sugar is. And then that's when you should feel like you hopefully have an understanding of this yield keyword. Okay, before we actually get started with all of that today, are there any questions?
I have a quick question. I'm a little confused what you mean by the control flow goes back, or?
Yep. It's a great question, and haven't actually explained what that means yet. So good to be confused about that. In order to explain what that means, we'll have to see exactly what these two magic methods are doing. So yes, good question. Okay, so we're gonna go back over here to the terminal, and we're going to create our, we'll call it iterables.py file. And inside of this file is where we will do our examples of these iter and next magic methods, and then the yield keyword. And what we're going to do in this file is we're going to implement a data structure that contains the numbers in the factorial function. So the factorial function, recall, is just, so if we have define a normal factorial function in, I think we started doing this last time, do something like ret equals 1, and then for I in range of 1 to n plus 1, ret times equals I, return ret like this. Now down here, Python 3 dash I iterables, and we can do, say, factorial of 3 is 6, factorial of 10 is this big number, and these factorials grow really, really fast as you get bigger and bigger numbers right here. What we want, so this factorial function sort of just returns one thing, but we somehow want to return like, or a container that contains all of the factorial numbers. And anytime you're thinking in the words container or thinking in the words data structure, this is where the class keyword comes in. That the class is somehow contains a bunch of things inside of it. And we're going to call our class factorial iter like this. And we'll see exactly why this pattern is factorial and then iter in a second. But one thing that we have seen before that we mentioned last time is that classes in Python, it's customary to name them with uppercase names and all non-class variables to have lowercase names. So normally it would be, this is what we'd call a camel case because it looks like a camel with all these humps with uppercase letters. Normally we would use snake case in Python like this because Python is a snake, and so we use snake case. But in classes, Python makes an exception because they're special somehow, and we use camel case. And we'll have a our constructor like this. And so at this point, this class kind of doesn't do anything. And I'm going to, inside of this class, basically every variable that's inside of this function over here, every variable, I'm going to create a attribute in this class for that variable. So there's two variables up here, this ret variable and this I variable. We'll do self.ret equals 1 and self.I equals 0, like this. It'll be, yeah, there's a lot with these classes. One of the things that's confusing about the classes is that it's not quite as step-by-step as, say, creating a function is. That with creating a function, you just start at the top, go step-by-step down, and each step kind of follows immediately from the previous step. For classes, it's not quite as straightforward as that you really have a lot of different kind of moving parts as part of this class. And so at this point, it's not necessarily obvious why I've done this, but it will hopefully become more and more obvious as we fill in more and more of these steps. So this is just a constructor at this point, same as the constructors that we've seen before. And when I call factorial iter, it'll call this function, creating these two attributes inside of my factorial iter object. This next magic method is sort of the new part of this class, something that we haven't seen before. And what this next is going to do is, the purpose of this next is to return the next factorial number in our sequence. So, in other words, the factorial number corresponding to position I, or self.I. And so we'll have basically similar code that we had up here. I'm going to do something like self.ret times equals I, and here I plus equals 1. This I plus equals 1 is similar to what's happening inside of this for loop right here, that every time we go through another iteration of this for loop, I is going to be increasing by 1. And here in this self.ret, every time the contents of this for loop is happening, this self.ret is being multiplied times I. And then down here, I'm going to do a return self.ret like this. And in order to see what's going on with this, I'm going to rerun this down here, and I'm going to create a factorial iter object. So I'll say x equals factorial iter like that. I have name self is not defined because I have a typo up here. Line 13, so 13 GG F parenthesis A L like that to get that L inside of here to fix that typo. And now down in the bottom, Control D to get out of Python, up arrow to get back to this command, enter, up arrow back here, and we fix the typo and things are working. I'll just go ahead and hit X right now to see it all by itself. And we get this kind of gibberishy looking thing because we haven't yet defined what a repr function for this factorial iter object would be. So it's not telling us the contents in any meaningful way of this object yet at this point. Now that we have this, we're going to take a look at what this next magic method does. But before seeing what's magic about it, we're just going to call the next method by itself and see what happens. So if I were to do self dot underscore underscore next like that, let's see, I have a, oops, it's not self dot underscore underscore next because I'm not inside of the function. Within here, it should be self, but outside of here, it's x that I want to be referring to. So it's x dot underscore underscore next. And here you can see that the first thing that's happening is I'm getting this unbound local error. This is one of those really common errors that you're going to see while you work with classes. And this happens whenever you have a variable that you should have put self dot in front of it, but you did not. So if you ever get this unbound local error, that probably means that you have a variable that somewhere you forgot to put the self dot in front of it. And so here, when I just do I by itself, this is a normal variable, a normal local variable inside of this class, but I actually want it to be referring to the I that's sort of part of the class itself. And so I wanted this to be self.I like this. on both of those lines. Down here, Control D, up arrow, reload this, redo x equals factorial and x dot next. And you can see that it prints out the number 1, then 2, then 6, then 24, then 120, 720. And every time I call x dot underscore underscore next, it's going to give me the next value in the factorial. The reason it's going to give me the next value in the factorial is because it's doing the same code up here that's calculating the factorial. That this line right here is sort of like what's happening in my constructor. Set ret equals to 1. I also have to define this I variable because the I is going to get defined right here in this for loop. And then this next is sort of like the contents of this for loop, what happens every time the for loop gets iterated. And so these two lines right here correspond to the sort of semantic meaning of what happens in this for loop. This self.ret is exactly equivalent to this line right here. And then this I plus equals 1 is exactly what this range is causing the I to be changing in each line. So at this point, hopefully exactly how these numbers are getting computed when we do x.next is should be making sense to you. And so are there any questions about that, where these numbers come from, why it's 1, 2, 6, 24, whenever I do x.next? Okay, one maybe more example that I'll do, which will maybe help illustrate the power of classes a little bit more, is I can create another one of these factorial iter objects. So here, this x has computed up to 720 like this. But now if I were to do y is going to start over at the beginning. That this y has its own I index inside of it and its own ret variable inside of it. So y is going to be keeping track of the factorial numbers independently all by itself. And we can calculate some more factorials with y like this. And then if I want to go back to the x, I can just change that y to an x, and it picks up where the x1 left off, and I can calculate some more factorials like this. One of the advantages of classes is that you can have many different instances of this class, each with different contents. So in this case, we could have many different sort of these data structures that are each independently computing factorials. Okay, so we've defined our factorial iter class and created these two functions inside of it. We know what the purpose of this init constructor magic method is, but we haven't yet talked about the purpose of this next magic method constructor is yet. And so we'll do that next. And this one is a very simple one, that this line right here, x dot underscore underscore next underscore underscore parentheses, is equivalent to saying next of x, like this. So next is a special built-in function defined essentially like define next of x as x dot underscore underscore next, like this. And so this is just a shorthand, convenient way of writing out this whole thing like this. And that's all that this magic method does, is it lets this global next function that's defined like this call the function in a slightly more convenient way.
Hey, Mike.
Yes.
So at any point when you're doing the iterations on X or Y next, does each class object still only have the two attributes of ret and I, and it doesn't keep track of previous iterations?
Exactly. So the question is that, let's say we're looking at our X class right now exactly as it is. The question is, does it somehow store the history of the previous values of ret and I, or is it only the ones that it exactly has right now? And the answer is that it does not store any history at all. It only stores exactly what it has right now. That these ret and these I variables behave exactly the same way as an ordinary Python variable does. And so when I do I plus equals 1, we've changed that I forever. It's no longer equal to whatever it used to be, and there's no way to figure out what it used to be. And similarly, when we modify ret, that value is changed forever. There's no way to modify it or to figure out how it was modified and sort of go back in time.
I have a question.
Yeah, go ahead.
So the reason that we define the underscore next function is so that we can then call the non-underscore next function, or like, I'm just confused where did the non-underscore next function come in?
Yeah, this is a good question, and this is yeah. So the question is, in some sense, what's the difference between this function here and this function here, or this function here and this function here? And the answer is that this interface into this next function exists only for historical reasons in Python, and so in practice, nobody's ever going to be calling next of x or underscore next underscore x like this. Yeah. So in some sense, this magic method, there's not very much to it at all. That if this function by itself sort of makes sense to you, then yeah, this function right here is not important. In terms of why this function is a magic method, this is what it does. That it has this next function that's a global function. It's defined exactly like this. And you can call this next function right here without actually doing x dot. You can do it just like this. We're gonna, yeah, so then sort of like, what's the purpose of this next function in sort of like a bigger picture philosophical sense? We'll talk about that here in a little bit, but this is actually going to be related to for loops. That when we have a for loop that does something like for x in 1, 2, 3, 4, 5, what's going to happen here, and maybe I'll break this out into 2 steps, xs equals 1, 2, 3, 4, 5 like this, and then do something in here involving x. Whenever you have a for loop that uses this in construction right here for some variable in some other variable, what it does is it calls xs dot underscore iter like this. This will return an iteration object, an iterable object, and the iterable object must have the underscore next method defined within it. So yeah, this is where we're going with this is we're going to be defining data structures that you can use inside of for loops with this construction. In order to do this, we have to have this next function, but there's still more steps that we have to fill in the gaps with that. So I think, yeah, what we should do next is start filling in those gaps. And if you still have questions about this part right here, hold on to those until we'll come back full circle and revisit this after we fill in a little bit more gaps about what's going on. So this class right here, this data structure right here, this is the class that stores the information about a current iteration through the data structure. So a current for loop that is currently happening through the data structure. But we still have to actually define what the data structure is. So class factorial like this, and def init self And here, actually, we're not going to need to have anything. We can just pass. And there's another magic method called iter, I-T-E-R, like this. And this will return our factorial iter object. Anytime you want to have a data structure that supports for loops, this is the sort of the syntax that we'll be using. So factorial is the data structure that supports for loops, and it supports for loops. We know it supports for loops because it implements the underscore underscore iter magic method. Because it implements this, we know it's going to support for loops. And the thing that the iter returns is the particular class that's going to contain the information that's needed to do the for loop itself. So factorial iter right here. And you'll notice that I am returning the, I'm actually constructing one of these objects like this. And yeah. In order to, let's see, before I go on to actually showing what this looks like inside of a for loop, I'm going to come down here, we'll reload this in Python. See, there's no error messages. That's good. And now let's do, call it fac for factorial equals factorial like this. And so if I just do fac like this, you can see we get this sort of junk object like this. If I were to do fac dot underscore underscore iter underscore underscore like this, that will give me a factorial iter object like this. I could do something like x equals that, and now do x dot next, and repeat that multiple times. When we come down here, I'm going to actually make this as a for loop now. Let's go ahead and comment out all of this right here. And we'll do, so for I in, we'll do it like this, f equals factorial, a little bit more step by step, for I in f colon, print the value of I like this. And I'm also going to add a line down here of if I is greater than 10,000 break, so that we eventually stop. Come up here, rerun this, and we can see that it's printing out the first numbers in the sequence of factorials until we get something that is greater than 10,000 and it stops. Technically what's happening here, anytime you have a for loop in Python, so whenever there is a for loop in Python, first creates a temporary variable. We'll say like temp equals, and then we'll do f dot iter like that. And then we'll do something like while true. Here, since we're doing I in f, we'll do I equals temp dot underscore underscore next underscore underscore like that. And then print out the value of I, and if I greater than 10, 1, 2, 3, break. This for loop up here is exactly equivalent to this while loop down here. That the way this for loop is actually implemented, and the way all for loops in Python are implemented, is that it calls the iter object like this to get the actual thing that it's going to be iterating over, the object that it's going to be iterating over, and then we use this next object, this next method inside of the iteration object that I've called TMP to get the next value of I like this. And so we'll break out of this, rerun this, and you'll see that we get the exact same values. This first one up here corresponds to this for loop right here. the second one down here corresponds to this while loop down here. And so at this point, this is, I don't know, there's a lot of pieces going on here that doesn't seem like we're getting very much value out of this. But this is exactly actually how the range function is implemented in Python. That the range function, it turns out, is not a function. The range function is a class, just like this, that implements a function iter. The iter function returns an iteration object. That iteration object has a next inside of it, and that will give us the next value in your range at every particular iteration of the for loop. If you've ever used the enumerate function in Python, enumerate is implemented similar. It's not actually a function, it's a class like this. When you do your looping over a list, something similar happens, that you're looping, this is the list right here. The list has the iter magic method defined inside of it, and that has a list iteration object. The list iteration object tracks the index into the list and returns whatever the next index in that list is. So anytime you have something that you might want to do a for loop over, whether it's an actual like container data structure like a list that contains things inside of it, or whether it's something more abstract like a range or an enumerate or a factorial, anytime where you just have sort of a sequence of events that you're generating one by one, you might want to loop over that. And this is the sort of pattern, programming pattern that you use to do that. Let's see. This is a good stop, a good point where hopefully things are starting to kind of connect together for everybody. And so if you do have questions, now is a good time to ask them. But there's not really any remaining gaps left.
I have a question about your use of break.
Sure.
And the first time you use it, you put the semicolon, and then the second time you didn't. I was just wondering what that semicolon does.
That's a good question. So in Python, semicolons are for when you want to have multiple commands on the same line. So normally if we were going to say like print A and print B, you would separate them by lines. If you wanted them on the same line, you can put a semicolon like this. Other programming languages require a semicolon at the end of every single line. And my fingers were in the habit of just, after you type the word break, you put in a semicolon because there are, I'm used to typing break in those other programming languages. So it's entirely equivalent to this, same thing. Good question. See, there's a question in the chat about why is this divided into two separate classes, and is it possible to combine them into just a single class? And the answer is that if you look online at a lot of tutorials for, so these are called iterators that we're talking about right now. If you look online for tutorials about iterators, they will often combine them into a single class. And we can combine these two into a single class by, if I were to down here, do something like this, and now return self, then now this class right here is both the data structure that sort of describes what we're iterating over, and it's the container that does the iteration. It happens to work correctly in these simple cases, but in general, it does not work correctly. And in particular, for any container that actually contains data inside of it, so like a list or a deck, it's not going to work correctly. And so my sort of general recommendation is to always have two separate classes, even for the situations where it could work correctly. I always do two separate classes, just this sort of base class, the actual container, the thing that's supposed to contain the data, the factorial information, and then this class down here that actually contains the information related to the iteration.
Could you create like a global class and then contain those subclasses within it?
I'm not sure what you mean by a global class and a subclass.
like, for example, let's say there is a larger class that contains the class factorial iter, yeah, like that.
Something like that. Okay. So this is also possible to do, and this is will compile. It would compile and work fine, except that I have stuff down here that's actually referring. Where is it? Line 19 factorial iter. It'd have to be self.factorial iter. There we go. So this works fine. It's very very rare in Python to for people to create classes inside of classes this way. The technical name for what I would call this is a locally scoped class, or a local class inside of this class right here, in the same way that when we created functions inside of functions, those are local functions inside of the global function. This is possible to do, and I'm sure some people do it. My personal preference would be to essentially always have classes global, because it makes testing much easier. Now that these things are global, I can write tests just for this class sort of directly without having to integrate this class at all. And in a lot of cases, maybe it doesn't make sense to write tests that way, and so people put it as a local class. I guess that it comes down to a stylistic thing. These are all great questions so far. Any other questions? Okay, then at this point, I'm going to take a quick break from looking at Python code, and we're going to take a look at what your homework assignment is for this week, and we'll see how the part of your homework assignment maps onto what we've just done in class. So I'm going to switch over to our notes, and the first thing that I want to do is come down to these instructions for the homework/lab this week. So this week there is no separate lab, and the homework is mostly the same as your normal homework assignments, previous homework assignments, except that I do not want you to fork the homework assignment this week. Instead, this week you're going to actually create your own repo from scratch, and you'll have to manually put the contents of my repo into your repo, following these instructions down here. The reason for that is because over the next few weeks, probably 5 to 6 weeks in this class, so the majority of the rest of this course, we're going to continue using the same containers repository for all of your assignments. And every assignment is going to add sort of new containers, new data structures into this that you will be building. And kind of that's the main purpose of what we're going to do throughout the rest of this course is you will be building and designing your own data structures and putting them into this library. Throughout the next homework assignments, I'm going to ask you to do some slightly subtle things involving Git and Python repositories that will sort of simulate the process of creating like a full-blown Python repository project from scratch yourself. And so part of that is that you'll need to have it not be forked from my repository. So if you have already forked it, just go ahead and delete it and then create your own. Also say that these containers that we'll be working on using this class sort of construct in Python, our big picture goal is that, so we've seen that like binary search is the great way for getting information out of a sorted list, and sorting is required for binary search. But the downside is that you have to do the sorting. And then if you get new data into it, you have to resort your containers. We're going to be building up to this sort of magical container called a B-tree. This is the container that is actually what Google uses every time you do your searches in Google search. They use a B-tree to get access to the queries that you're looking for. And you're going to be implementing that in this repository here. And what we'll see is that not only in the B-tree, not only is lookups fast, not only it's as fast as binary search, login time, but inserting into the containers also fast. It also takes login time. So as Google's crawling the web, adding new web pages into the containers, they can do that very efficiently in microseconds because of this login behavior. And we're building up, you'll be building up to a library that implements that, that data structure. We won't talk too much in this class about actually using that data structure, like what you can do with it. For that, you'd want to take the big data course that's sort of the follow-on to this course. The main purpose of that course is actually applying this cool data structure to all sorts of different applications. Okay, so yeah, there's this containers repository up here. And inside of this containers repository, there's another folders called containers inside of that. And this is where the source code is that you'll have to actually modify. All of the sort of future programming assignments will be additional files that are inside of this containers folder inside of the containers repository. There's two of them, Fibonacci and range. So we'll start with Fibonacci. And let's zoom in to make this a little bit bigger. And at the top, I have a few different implementations, sort of classic implementations of the Fibonacci numbers. You don't have to modify this code in any way. This is just serving as a reminder to you of different ways to compute the Fibonacci numbers that you can use as a reference. And these are also used in the test cases to make sure that your code below is correct. And then down here, you'll actually have to implement some generators that generate the sequence of Fibonacci numbers. And so here we have class fib and class fib iter, and these correspond exactly one-to-one to this factorial and factorial iter. So for both of those classes, you'll have to, or I guess for the fib class corresponds to factorial, you'll implement the init and this iter function, and then factorial iter, you'll implement this init and this next function right here. So it'll be virtually the same code, except that you'll replace the logic from how to do a factorial for the logic to how to do a Fibonacci sequence. Have any questions about that?
I have a question about the factorial class.
Yeah.
It just seems wrong to have like a pass in the dunder init method, and I was wondering if you could say some words on that.
Let's see. So it would be equivalent to do this, and that is also 100% correct. You could take away the init function because it has nothing inside of it. It only has pass. And you could actually take away any function that only has pass inside of it. This is sort of, whenever an init function is not explicitly given, this is the implicit definition for init and just what will be used. So yeah, either way is correct and not wrong. The next thing though that I wanted to talk about is that it'll be related to this init function and something that we will need the init function for. So we are going to add something inside of it besides just pass. And that's related to this down here. That at this point, our for loop here is still kind of a little bit awkward to use because I have to explicitly put an if statement down here, explicitly put an if statement right here saying to stop after 10,000 iterations, or after the number I gets to 10,000. And that's not how we're used to writing for loops. That's not how, like when you use a range construct up here, that's not how this works. You don't need an if statement if you're using the range. And so let's take a look at how that is actually implemented in Python. How can we make it stop after a certain number of iterations? And in order to do that, we'll pass in a variable here, defaulted to none. There we go. And self.in equals n, like this. And here in, the semantics of in is the number of iterations we will run. And if in is none, then we will run forever. And in order to sort of know the number of iterations that we're going to run, we need it both in this factorial object and in the actual iteration object. The iteration object needs to be able to reference, needs to know how many iterations to run for. And so down here, we can do factorial iter, and we'll pass in like this. And here we'll also take the in parameter in right here. Here, up here, I'm going to give it a default parameter of none. The factorial iter is never, it's not designed to actually be invoked, created by itself. And so I don't need to create this sort of convenience default parameter like this. And I'll just leave it as a required parameter. And then down here, I'll do self.in equals in. The real main modification comes inside of this next function down here. And down here, we will say if in self.in is less than or equal to self.i, then we're done. We should stop. And we should only do this other stuff down here when our I is not yet reached up to the value of in. So that begs the question, how do we signal to this next function? How do we signal to this next function that we're done? And that's where another form of exiting functions is going to come into play. So back down to our notes. There we go. Oh, one more back. And scrolling down to the bottom of this file again. So no return. We've seen yield, but haven't fully discussed it. Keep that on pause. This raise one is the function that or the keyword that you need to exit out of this next function, exit out of this next function in a way that's going to stop the iterations. And we'll raise, and the thing to raise is stop iteration, like this. Stop iteration is called an exception. So we say we are raising an exception. In other programming languages, exceptions have other names like typically errors is the most common thing to call it other than an exception. And in other languages, instead of raising the exception, you might throw the error or throw the exception. And so you will see people you'll see people in the Python world using the words exception and errors interchangeably, and the words throw and raise interchangeably, just because other programming languages use those other words. This stop iteration right here is a class. It's a special class that has certain magic methods like this implemented directly for exceptions. We haven't talked about what those are yet, and we won't today. It'll be probably a few weeks before we get to talking about those. But the key thing at this point is just that when you're inside of an iteration, an iterable object, and you're calling the next function and you want to signal, don't just end this next function, but end the entire iteration, basically end the for loop, then you raise stop iteration like that. So if you return from next, then it actually gives out a value. If you raise stop iteration, it ends the for loop. Come down here, close this, reload it. Let's see, name in not defined, 23, GG, return factorial of in. Once again, I've forgotten myself dot up here. Very common thing to do. Less than or equal not between none type and int. Go to line 37, GG. So here, what's happening here is when I wrote this, I was assuming that in was equal to an integer, but in is actually by default none, and you can't compare none less than or equal to an integer. So if self.in is not none and this will first check to see that it's not none and only do this condition over here if it is in fact not none. So if you get This is something that you will also have to do on your Fibonacci assignment. So your check condition is going to look something like this. You'll have to check to see that this parameter is not none before doing the integer check. And rerun this, and now it works. And now if I were to say, do something like not fib, factorial of 10, it's going to give me this factorial object like this, but I can convert it into a list and it'll give me the first 10 items, the first 10 factorials, kind of magically this way. I can get the first 100 like that. And you can see these numbers are very big. I can come down here, I can change my for loop so that instead of, let's go ahead and just comment out all of these blocks so we'll be able to easily see what's going on, and do something like for I in factorial of 10, I at P to print it, come down here, and now print out the first 10 factorial numbers this way. This, yeah, it might seem a little bit artificial to you to be doing this with factorials, that why don't we just create the factorial function, that seems easier, or why don't we just return a list of factorials. It is a little bit on the artificial side of using the factorial function, really just getting you into the mechanics of being able to create these magic methods and this whole framework. But this is also something that people do in fact do. So you can find libraries on Python libraries that will say you can loop over the digits of pi, just putting the pi generator object right over here, or all sorts of different mathematical sequences that are useful for various different operations. And these do have useful applications in lots of mathematical programming. Are there any questions about how we got rid of this if statement and were able to incorporate it into this parameter that gets up here?
I'm still a little confused on the raise stop iteration piece.
Mm-hmm. Let's see. So the key thing at this point to take away from the raise stop iteration is that you just put this line right here when you actually want your iteration to end. So when you have a condition that means that you should be done with the iterating, then you raise stop iteration. Exactly what these things are doing, we haven't talked about yet, and that'll be like a week's worth of lecture that explains some point in the future what these two things are doing in detail. But at this point, you just know that there's two ways to get out of the next function, and one is to return the value that you want next. But if you're actually done iterating, then you have to raise stop iteration. Did you have a more specific question than that, Jonathan, or?
No, that's good. Thank you.
Okay. Raj, go ahead.
Yeah, is it possible to use break instead of raise stop iteration?
Great question. The question is, can you use a break statement here, something like this, instead of raise stop iteration? And the answer is no. That this break statement, you're correct that it does break out of for loops like we were doing down below, but it stays within function scope and it can't break out of a for loop that's outside of the function that you're currently inside of. So you do have to raise stop iteration. There are other things that you can raise right here that do slightly different things, but you must raise something in order to end the iteration.
Got it, thank you.
Mike, I had a question about, I had a question about the, I'm a bit confused about why the factorial directly gives a iterable. I thought we had to use the iter magic function. I think I missed something there.
So is your question about this line right here, line 50? Like why we're not calling the iter function? Okay.
Yeah.
So let's see, rather than talking about these lines, I'll go back to these lines down here and see what's going on. Maybe the first difference between this line this for loop right here and this for loop right here is that I just combined this f equals factorial into like this. And you can see that here, when I'm using the for loop syntax, I'm not explicitly calling the iter magic method anywhere. That I use this syntax, I'm not calling the magic method anywhere. Let's just see that this still works. That, come down here, oops, line 62. Here we'll do factorial dot iter, rerun that. So when you use the for loop, you never have to explicitly call the iter magic method. What the for loop does for you internally, the for loop is implemented with this pattern right here. It first creates some sort of temporary variable where it's taking whatever you have inside to the right of the in operator here, and it's calling the iter magic method for you on that. Then inside of the while loop, it's calling the next magic method. So for automatically calls both the iter and the next magic methods for you.
Yeah, that makes a ton of sense. One last bit. So like, could we use like list and then factorial 10 if we don't have the for loop? I think there was an example where you said like list factorial.
So I did something like that.
Yeah, does it? Yeah, so it also subs in the with the similar to what the for loop is doing.
Exactly. So the way the list function here is implemented, this is actually not a function. This is the constructor for the list class, and the list class takes as a parameter something that you want to create a list of. The parameter, the only requirement of it is that it has the iter function implemented, that it's an iterable object. And so because factorial is iterable, list will internally use this sort of for loop construction to go appending one element at a time by calling this next one element at a time on this factorial object up here. Maybe one sort of gotcha with this sort of syntax right here is that if you say pass in none, which is, since we have a default value of none, equivalent to passing in nothing, then the factorial is never going to stop. It's going to go on forever and ever. And so this is just going to generate, it's never going to stop. It's going to try to create an infinite list that contains all of the factorial values inside of it. And so I have to press Control-C to do the keyboard interrupt down here. If you never, inside of your next, if your next never raises stop iteration, if we never raise stop iteration, then the loop will go on forever. So one of the main advantages of a for loop is that it's supposed to be guaranteed not to go on forever, but if your data structure is buggy somehow, or you do something with it that it never does the stop iteration, then the for loop can go on forever.
Hey, Mike,
Yes.
didn't we check, or why is the check of self.n not being none? Why is that not kicking in?
It is kicking in. So we pass in not none right here. So self.in self.in is equal to none because there's no parameter passed in right here. So self.in is not none. This evaluates to false. False and anything is false. So this whole thing is false, and we always go down into here. So whenever you have your parameter is none, which happens when you have no parameter, then you can never get inside of here, never get to the raise stop iteration, and you're always forever and ever and ever generating new values down here. Let's see, these have all been fantastic questions, but we have one last concept to cover before you're ready to do all of the homework assignment. And so I want to make sure that we cover that in the next 5 minutes or so. And if you do have more questions about these concepts right here, then I'll be available in office hours to do that. And the last thing for us to talk about is the relationship between these class methods up here and the yield keyword in Python. So here, this is sort of admittedly a lot of stuff. This is a lot of stuff to keep track of inside of your classes. And a lot of the questions that you all have been asking so far have kind of boiled down to like, is all of that really necessary? And the answer is, in most cases, it's not necessary. And the yield keyword is how we handle those cases where it's not necessary. So the yield keyword lets us simplify all of the stuff we did below into a simple function. And here's what I'm going to do. I'm just going to replace this return word right here by the word yield. And now this function right here is 100% equivalent. It's equivalent in every way to this factorial class right here. What this yield does is it internally, behind the scenes where you can't access it, is it creates a class. The constructor of that class contains just these sort of important things like in that you'll be doing the stopping conditions on. It also creates this iteration class. The values inside of this iteration class correspond exactly to all the variables inside of your function. So we have a ret and an I and an in inside of this function. And so we say this function desugars into this constructor right here at the very beginning, just defining all of these things like this. Then we have this next function, and the yield, whatever, yield ret, this corresponds to the return value of the next function. Yield, I'll say xxx is the equivalent to return xxx inside the next function. And then when we have raise stop iteration inside of next, raise stop iteration is equivalent to return none inside of this function right here. Let's see, and when I replace this return with yield, I also wanted to indent it like this because it's the contents of this for loop that are being returned every time inside of the next function. And so the yield should happen immediately after we multiply ret times I. Then once we're done with this for loop, that's equivalent to making the condition of the raise stop iteration if statement true. Then we'll come down here, and if you don't explicitly return a value, then your function implicitly will return none. I'm going to go ahead and open this up in Python. And now we have this factorial function like this. Let's see what happens if I do factorial of 10. We get that it says generator object factorial. So we get this sort of nasty looking thing that is similar to what we would get if we did factorial 10. And we can do something like list. So this is a uppercase factorial right here. This is what we've seen before. Now let's do that with a lowercase factorial, and we get the same exact results. So this yield syntax, sort of wrapping your head around exactly what is it doing internally, takes kind of takes like your brain melting and reforming a couple times. And it's okay if you feel like this is somehow magic, like what did this do at this point? But what it's doing is it's just taking this factorial function. We say that this function right here, this 5-line function is syntactic sugar for this giant expansion of the sugar down here. And we say that this giant thing down here is the desugared version of this function right here. On your homework assignment, let's come back up to your homework assignment. Under containers, under Fibonacci, you will have to first implement the class version of this Fibonacci generator, and then you'll have to implement a yield version of this Fibonacci generator. Both fib yield and fib uppercase F are going to do the exact same thing. They'll just be implemented slightly differently. And you'll see that the implementation of fib yield using yield, you can basically just take this function right here, replace return with yield, and indent it into the for loop, and you'll get the correct thing. And then you'll also have to work on the desugared version up here to get you some practice with both of those, the desugared versus the sugared form. Inside of the range.py, you'll also have to implement the actual range function used in Python. So it takes in 3 parameters, gives you back a, so it doesn't give you back a list, it gives you back a generator object. We can convert that generator object into a list to actually view the contents of it using functions like this. And you'll have to implement this range function using that yield syntax to generate appropriate lists. One last note about this is that, so my implementation of this range function, I was able to write a really terse 4-line version of this function. So it's possible to do it really compactly like this. My easy to read version is 15 line long, but I will also want to take you to the actual implementation of this range function that Python uses right here. Python's open source, so we can just look at the source code whenever we want to see something. And here's the actual implementation in Python. Python is, for efficiency reasons, Python implements this range function using C instead of Python. And so it's not going to be 100% equivalent in terms of runtime, your code and this code. And you can see that this implementation is, wow, it's a lot of lines long, almost 1,500 lines long. And I was able to reduce essentially 1,500 lines of code down into like 4 or 15 lines of code. And this is a very common thing with Python versus other programming languages like C, that because Python has all of this syntactic sugar, things like this yield keyword and list comprehensions, other things that we've seen so far, and a lot of things that we haven't seen yet, we're able to take things that would be really, really large in a lot of other programming languages and make them very compact and small and easy to read. And that's one of the main reasons that people like Python. It's also one of the reasons that people don't like Python, because in order to understand Python, you have to understand a lot of extra syntactic sugar things that are going on, like this yield keyword that don't exist in other programming languages. Let's see, so that's everything you need for the homework assignment this week. Again, there is no separate graded lab, so I'll still be available tomorrow during the lab time to answer questions about either the this week's homework assignment, which is for the generators, or for the Twitter homework assignment. I wanted to explicitly have no extra lab work this week so that you'd be able to ask extra questions on both homework assignments, because we have sort of 2 out at once right now. Yes, so that's the end of class today. I'll see you either tomorrow or next week.
Thank you.
Good night.